Hi, my name's Andreas, and today we're going to talk about a 2017 paper called kAFL, Hardware Assisted Feedback Fuzzing for OS Kernels. Before we get into the paper itself, we need to build up some background, so we're going to start from the ground up. We'll cover exactly what fuzzing is, why kernel fuzzing is uniquely hard, and why existing tools fell short. And then we'll see exactly how kAFL solves those problems using some clever hardware tricks. So here's the roadmap for the presentation. We'll start with fuzzing fundamentals to make sure everyone has the same baseline. And then from there, we'll talk about why the kernel is particularly hard to fuzz. And then we'll look at how prior tools tried and where they fell short. Then we'll dive into kAFL itself, and then we'll finish at a analysis about its performance, impact, and its limitations. At its core, fuzzing is pretty simple. You take a target program, throw unexpected inputs at it, and wait for crashes. The diagram here captures the whole idea. Inputs go in, crashes come out, and we save the input caused by the crash so we can study why it crashed. Before I go further in though, I want to ask, why would this ever work? Why would randomly generated inputs find bugs that developers missed? The answer is that developers test the inputs that they expect their softwares to receive. Fuzzers tend to test everything else, and it turns out everything else is usually where the bugs are hiding. So the question is, why do we even bother doing this at all? First, software has effectively infinite possible inputs. No development team can manually test more than a tiny fraction of what a program might receive. Second, the bugs that slip through the gap aren't just annoying crashes, but they may be exploitable. Memory safety bugs like buffer overflows give attackers the ability to take control of your machine. And third, fuzzing finds these bugs automatically at scale without human needing to think of the right test case. And now the question is, how do we make our fuzzer as good as possible at finding those bugs? It really comes down to two levers: speed, which is how many test cases can you run per second, and test case quality, which is, are your inputs actually reaching interesting, deep parts of the program, or are they getting rejected immediately at the front door? These two things are in tension with each other, as smarter inputs take more time to generate, which means fewer iterations per second. And the best fuzzers usually find the right balance between these two. And kAFL makes its innovation made mainly in the department of speed over previous implementations. So how do we improve test case quality? The key insight is coverage guidance. Instead of throwing purely random inputs, we instrument the target binary to track which branches of the code get executed. If an input target if an input triggers a branch we've never seen before, uh, we save it and mutate it further. If it only hits code that we've already explored, we throw it away. Now, looking at this example, if our fuzzer generates random input and it never starts with A, it'll never get past the first check. Covered Coverage guided fuzzers steer the fuzzers towards inputs that unlock new code paths. This technique was popularized by a tool called American Fuzzy Lop, or AFL, which is the direct ancestor of kAFL. So here we have a simplified diagram of how the AFL fuzzer works in practice. The fuzzer reads from a seed pool of known interesting inputs, mutates one, and sends it directly to the instrumented binary. The binary runs, and as it executes, it writes coverage data uh, containing which edges are in the target program are hit, writing that into a shared memory bitmap. The fuzzer then reads that bitmap, and if a new edge was found, the input gets added back to the seed pool as a candidate for further mutation. Uh, and if nothing new was found, it gets discarded. And we can see another key aspect of this is uh, how is the fuzzer will fork new processes. In the actual implementation, it does this in a smarter way, but The basic concept is it spawns new processes that are separate from the fuzzer itself, and so then it won't uh, crashes in the instrumented binary won't take down the fuzzer with it. One more piece of information before we move on is how does coverage actually get measured? AFL instruments the target at compile time. You give it the source code and it compiles a special version of the binary with tiny counters inserted at every branch point. And when that branch executes, the counter increments in the shared memory and the fuzzer can see it. An important aspect about this is that you need the source code of what you're trying to fuzz in order to do this. And without the source code, you can't get coverage, and you're basically demoted to blind random fuzzing with no guidance at all. And this aspect is this problem is one that kAFL tries to solve. Now we get into why we actually care about fuzzing the kernel. The kernel at its core is the privileged component of the operating system that acts as the primary bridge between the software applications and the physical hardware. So it's basically the lowest level software that exists on the computer. So looking at this privilege ring diagram, we can see our applications live on the outside in ring 3, and the kernel lives in the center at ring 0. Everything on your machine goes through the kernel, every application, every driver, every hardware access, and while a bug in a user space application at the ring 3, what a bug in the kernel is catastrophic. A vulnerability gives an attacker the same privilege level as the operating system itself. They can read any memory on the system, bypass any security control, kill any process, and own the machine completely. There are no guardrails down below ring 0. And this is why kernel bugs are the most valuable bugs to exploit. Mental problem. The fuzzer lives, our fuzzer application lives up in user space at ring 3, while the target we're trying to fuzz, the kernel, lives down in ring 0. And these aren't just logically separate layers, they're architecturally separated by the CPU itself. And so ask yourself, if you have the fuzzer and the kernel that you're trying to target on the same machine, what happens when your fuzzer finds a crash? So now we get into why fuzzing the kernel is hard. Uh, so first, when you have the kernel the kernel you're trying to fuzz, or the fuzzer trying to fuzz its own kernel that's running on the same machine, when it finds a crash in the fuzzer, it breaks everything. Because there's nothing below the kernel to catch the crash, you lose the state in your fuzzer, and you have to fully reboot. And second, the kernels aren't always open source, so you lose that instrumentation that we talked about earlier. With an open source kernel, uh, like the Linux kernel, there are tools that exist to instrument that and provide coverage hooks into that. But something like Windows or Mac OS don't provide coverage feedback for that. Uh, and Another problem is that you can't fork the kernel like we were doing before with our user space processes. So the questions are, how do we make the fuzzer independent from the kernel that we're testing, and how do we make it fast? Because remember, the throughput of our fuzzer is pretty essential to finding actual bugs. The AFL loop and walk through each step with a kernel input as the target. So we can see everything pretty much just breaks down here. The fuzzer can't fork the kernel because the fork model doesn't apply here. Uh, we can't deliver inputs via standard in or a temp file because there's no equivalent interface for kernel subsystems. The kernel can't write coverage to a shared memory bitmap without a source and instrumentation, and if the kernel crashes, the fuzzer dies with it. There's no recovery. Every step of this just breaks, and this is why we need a fundamentally different architecture uh, when we want to uh, fuzz kernels. Attempt at kernel fuzzing was Triforce AFL. The idea is to run the entire target operating system inside of QEMU, a software emulator. QEMU has a component called the Tiny Code Generator, or TCG, which translates the guest CPU instructions into host instructions in software, one block at a time. Triforce AFL then hooks into this translation process to record which blocks execute, giving you coverage feedback without needing the kernel source code and recompiling it. Uh, and since the kernel runs inside of QEMU, a crash inside the guest just pauses the emulator, and your fuzzer keeps running. Uh, this approach solves the problem of uh, the the crashes in the kernel crashing the fuzzer, but the full software emulation is very slow, and on top of that, the TCG hooks are tightly coupled to Linux internals, which makes this practically Linux only. That the paper mentioned is one called syscaller. Syscaller takes a completely different approach, and instead of dumb input mutation, it uses handwritten grammar specifications that describe Linux system calls in detail, what arguments they take, what types are valid, how the calls relate to each other, and from these specs, it generates structured, semantically valid syscall sequences that actually make sense to the kernel. It runs the kernel inside a VM for crash isolation and uses a kernel coverage uh, called kCOV for feedback. For Linux fuzzing, syscaller is arguably still state of the art today, but there are two areas of issue. Uh, One is that writing accurate syscalls specifications requires expert knowledge of your target kernel, and furthermore, it primarily only works for open source operating systems due to the need for the kernel to be instrumented. We just saw Triforce AFL is slow and Linux only, and syscaller requires enormous manual effort and is tied to Linux. What does our ideal kernel fuzzer look like? We need speed, so we can run thousands of iterations per second. We need binary only operation, so we can target closed source systems like Windows and Mac OS without touching the source code. We need crash tolerance, so a kernel panic doesn't kill our fuzzer. And we need OS independence, so the same tools will work across different operating systems. These four goals directly address the specific failures of prior work, and is what kAFL hopes to solve. The first key building block is virtualization. kAFL runs the target kernel inside a KVM virtual machine using Intel VTX hardware virtualization. This is fundamentally different from Triforce AVL's software emulation. Instead of translating instructions in software, KVM lets the guest kernel run directly on the CPU at native speed using hardware virtualization. The hypervisor layer sits below the guest operating system and can observe everything that happens inside the VM, including crashes, without being affected by them at all. A kernel panic inside the virtual machine is just an event that the hypervisor observes from the outside. The host machine keeps running, the fuzzer keeps running, and the VM gets reset to a clean slate. The second key building block is Intel Processor Trace. Intel PT is a hardware feature built into modern Intel CPUs that records the control flow of executing code. Every branch taken, every call, every return as a stream of compressed packets that gets written directly to a memory buffer. The CPU does this entirely uh, in silicon with minimal performance overhead, and this is kAFL's core insight. We don't need to instrument the kernel source code to get coverage coverage feedback because the CPU will give us that same information for free. No source codes required, and we don't need to recompile the operating system or kernel, and this will work on any operating system, closed source or open source. So how do these pieces connect? kAFL introduces two custom components. KVM-PT is a modified version of Linux's KVM hypervisor that adds the ability to enable and disable Intel PT tracing for a specific virtual CPU. This means that traces are isolated to just the guest kernel's execution, and the host's activity is not mixed in. Uh, QEMU PT sits above KVM-PT in user space. It sends commands to stop and start tracing around each fuzzing iteration, and when a trace comes back, it's responsible for decoding those raw PT packets into something the fuzzer can actually use. So here's our full pipeline visualized. The CPU produces raw Intel PT trace data. KVM PT captures that trace data continuously for each virtual CPU. QEMU PT decodes the raw trace data in user space into basic block information. Uh, and then a filter step removes non-deterministic basic blocks, things like interrupt handlers that execute randomly and would pollute the coverage bitmap with noise. Finally, kAFL uses the standard AFL coverage bitmap to detect new behavior. Uh, each component in this chain does exactly one job, and this clean separation is what makes kAFL uh, fast and reliable. Put this all together in the complete fuzzing loop. kAFL generates a mutated input and copies it into a shared memory buffer that the VM can access. It enables Intel PT and signals the in-guest agent via a hypercall, which is a special instruction that traps from the guest directly into the hypervisor. The guest receives the input and delivers it to the target kernel. This executes at almost full native speed while Intel PT traces every branch in hardware. When execution finishes, a VM exit fires. kAFL disables PT, collects the raw trace. And then QEMU PT then decodes it into edge coverage, and then the kAFL process will update the coverage bitmap. If the kernel crashed, the VM is instantly restored to a clean snapshot, and the crashing input is saved. And if new coverage is found, the input goes into the seed pool for further mutation. So here's a look into the performance of kAFL and how it compares to Triforce AFL. So we can see that Triforce AFL manages 150 executions per second with a single process and 315 executions per second with 8 parallel processes, while kAFL hits 6,830 with a single process and 17,100 with 8. Uh, so that's a large improvement over Triforce APL in the single threaded case and in the multi-threaded case. Uh, the difference here comes down to the emulation versus hardware virtualization. Triforce AFL is bottlenecked by software instruction translation, while kAFL's guest kernel gets to execute directly on the hardware. And more executions per second means more of the input space gets explored, which means more bugs will be found in less time. This graph shows the number of unique paths discovered over 30 minutes. kAFL reaches Triforce AFL's final path count of 123 paths in just 2.6 minutes and then keeps climbing well above it. And we can see that kAFL isn't just running faster, but it's also plateauing at a higher final edge count. Now, it's important to recognize that kAFL has two significant limitations. First, it only works on Intel x86-64 machines. Intel PT and Intel VTX are both Intel-specific hardware features. You can't run this on AMD or ARM systems. However, the same architecture may be applied if the platform-specific tools like KVM-PT and QEMU-PT are altered to work with AMD or ARM equivalents to Intel PT and Intel VTX. Second, the mutation strategy is completely unchanged from AFL. It's dumb with it's pretty yeah with it's dumb with bit flips, byte substitutions, random splicing. Now this does provide the benefit of independence from your target kernel, but you don't get the in-depth uh, exploration of logical bugs like you would with a implementation like syscaller. Now, despite those limitations, the results are concrete and impressive. kAFL found real, previously unknown bugs across 3 different operating systems. On Linux, a null pointer dereference, and memory corruption, air handling bug. On Windows, a division by zero. On Mac OS, division by zero and assertion failure. Use after free, memory corruption errors. The headline result here is that uh, kAFL was able to find bugs in Windows and Mac OS with a single tool, which no prior fuzzer could do with the same speed. Uh, and another key point to make is that this architecture does not only apply to fuzzing closed source kernels, but can also be altered to target any closed sourced binary. So, to wrap it up, kAFL makes practical kernel fuzzing possible by combining 2 hardware features in a clever way. Intel PT provides coverage feedback without requiring kernel source code, and KVM hardware virtualization with Intel VTX provides crash isolation at near native execution speed. Together, they produce a fuzzer that is fast, OS independent, works on closed source kernels, and survives kernel crashes gracefully. kAFL was a genuine step forward that directly influenced how the research community approaches kernel fuzzing to this day.